Okay, so picture the San Francisco skyline, but not the one you see today. I want you to think back to maybe 2005.
Right.
If you looked at it from, I don't know, a boat out on the bay, it had this really flat profile, almost like a tabletop.
It really did. There's this sort of invisible ceiling that all the buildings just stopped at, right around 500 or 600 feet. It
Yep.
was, yeah, it was uniform.
And that wasn't some aesthetic choice, was it? That was basically fear. It was a mix of anti-growth zoning laws, sure, but the real reason was, the dragon in the ground, the
Yeah.
San Andreas fault.
Seismic risk is the invisible architect of California. And for decades, the thinking, both in engineering and in city planning, was just shorter is safer, stay low.
But then you look at that skyline today, and that tabletop is completely shattered. There's this one single massive tower that just soars above everything.
The Salesforce Tower.
Yeah, 1,070 feet tall. It's the
Yeah.
heaviest building in the city, and it's sitting on what is essentially mud, Old Bay clay.
I mean, it's a geotechnical contradiction. You're putting the heaviest thing you can build on some of the absolute worst soil right next to a world-famous fault line.
So that is the puzzle we're going to crack today. We're looking at an engineering deep dive by Ron Klemencic, who was one of the key engineers on this. And our mission for this dive is to really understand this huge shift in how we build things, how engineers stopped using brute force, just making things stronger, and switched to intelligent flexibility.
It's this move away from prescriptive rules and toward performance-based design. It's really the difference between building a bunker that tries to ignore an earthquake and, say, a willow tree that knows how to bend and survive it.
So let's start with the stakes. Because I look at a skyscraper, I see a building, I see a view. But the building code, it sees something else. It sees a risk calculation.
Exactly. In our world, not all buildings are created equal. The code classifies them based on what happens if they fail. A storage shed, for instance, is low risk. The Salesforce Tower, on the other hand, that's classified as occupancy category 3.
Category 3, what does that actually mean? Is it like a hurricane category?
It's all about human life. The code looks at the sheer number of people inside. For Salesforce, you're talking about a vertical population of over 5,000 people.
5,000, that's a small town, just stacked vertically.
It is. If a warehouse collapses, it's a tragedy. If this tower collapses, it's a historic catastrophe.
So the code basically says this one matters more.
Right. It assigns something called an importance factor of 1.25.
Yeah.
Now, in the standard prescriptive code, the rule book most buildings follow, that number is a really blunt instrument.
How so?
It basically just tells the engineer, take the earthquake forces you'd normally expect and multiply them by 1.25.
So just make the building 25% stronger.
That's the mandate. Designed everything to resist 25% more force.
And to me as a layperson, that sounds logical.
Right.
If I want to be safer, I buy a thicker helmet, I build a thicker wall. Why is just being stronger a trap here?
This is where the physics gets a little counterintuitive. In a static world, stronger is better. But earthquakes are dynamic. And to make a building stronger in that traditional sense, you usually have to make it stiffer.
Okay.
More steel, thicker columns. You make it more rigid.
So I've built a rigid bunker. I feel pretty safe.
But the ground isn't rigid. When the earthquake hits, the ground is moving violently. And if your building is really stiff, it tries to fight that movement. It locks horns with the earthquake. And because it's so stiff, it actually attracts higher ground accelerations.
Wait, hang on. So by fighting the quake, you're actually pulling more of its energy into the building.
Precisely. You're inviting it to hit you harder. You increase the shear stress, that's the tearing force, and you put these massive, almost unmanageable demands on the foundation.
I need an analogy. Why does that stiffness lead to failure?
Okay, think of a big, mighty oak tree versus a willow. The oak is stronger, it's rigid, but in a hurricane, that rigidity is a liability. The wind energy has nowhere to go, it just builds up until snap. The willow, on the other hand, it seems weaker, but it survives because it yields. It moves with the wind. It dissipates the energy.
So the old code was basically saying, build an oak tree, but 25% thicker. And the engineers for this tower knew they needed to build a willow.
A 1,000-foot tall willow, exactly. A skiff tower of that height would create forces so high that the foundation just couldn't handle it. So this is where they had to leave the rule book behind and use performance-based seismic design, PBSD.
Performance-based. Okay, so that implies they're not just checking boxes, they're aiming for a specific result.
Yes. Instead of just following the recipe, add 25% more steel, they define exactly how the building should perform in an earthquake. And then they have to prove, through simulation, that it will perform that way.
But how do you prove that? I mean, you can't build a 1,000-foot tower and then just shake it to see what happens.
You can if you do it in the digital world. This is where we get into something called nonlinear time history computer modeling.
Okay, that's a mouthful of jargon. Let's break that down.
The key word is nonlinear. Standard engineering often assumes materials are linear, meaning they stretch and bounce back perfectly, like a brand new rubber band. But in a massive earthquake, concrete cracks, steel yields. That's nonlinear behavior. The model has to account for that damage happening in real time.
And time history.
That just means we're not applying a simple static push. We are replaying the actual second-by-second timeline of a real earthquake's ground motion. They built a digital twin of the tower and then subjected it to 22 different earthquake simulations.
22. That feels like a very specific number. Why not just one big one?
Because every earthquake is different, and the San Andreas Fault has its own unique personality. They used 2 suites of 11 pairs of ground motion records to cover the range of possibilities.
Earthquakes have personalities.
Oh, absolutely. The Salesforce Tower is uncomfortably close to the fault line. And that means it's susceptible to something called pulse effects or near-fault directivity.
That sounds like a weapon system from a sci-fi movie.
Kind of feels like one. If you're far away from a quake, you get this rhythmic shaking. But if you're right up close, you can get a pulse. This massive, one-time, sudden jolt of energy. It's like a whip crack.
So they had to prove the building could survive the whip crack.
Exactly. And they went even deeper. They used an analysis called conditional mean spectra, which, I mean, basically, buildings don't just sway back and forth like a metronome. That's the first mode of vibration. A tall tower can also ripple, kind of like a snake. That's the second mode. They had to make sure that whip crack wouldn't snap the tower in that second mode.
This level of detail is just, it's incredible. So under the old rules, the prescriptive code, what was the acceptable risk? If the big one hits, what are the odds of collapse?
The standard code generally accepts about a 10% probability of collapse in that extreme maximum considered earthquake scenario.
1 in 10. That frankly makes me never want to go into a high-rise again. Welcome to the office. There's a 10% chance of doom.
Well, it sounds high, but remember, this is for an incredibly rare event, something that might happen once every 2,500 years. But still, for the Salesforce Tower, using this PBSD approach, they weren't satisfied with 10%. They actually targeted a reduction down to 6%.
So they made it almost twice as safe by ignoring the standard rules. How? What's physically happening inside the building to absorb all that energy?
It's all about the core. The skyline of the tower is made of these massive reinforced concrete shear walls, maybe 24 to 48 inches thick. But the key is they aren't designed to be indestructible. They're designed for controlled yielding.
Yielding. That word usually means breaking. Why do you want part of your building to break?
In this context, it's more like controlled stretching. Think of the rebar, the steel bars inside the concrete. They design specific zones where that steel is actually allowed to stretch and the concrete is allowed to have some minor cracking.
It's like a crumple zone in a car.
That is the perfect analogy. If your car were a rigid steel box, all the force of a crash would transfer to your body. The crumple zone destroys itself to absorb that energy. The tower's core does the same thing. It takes the punch from the earthquake, dissipating the energy through controlled damage to itself, so the overall structure doesn't topple.
Okay, so we have a willow tree with a concrete crumple zone, but a willow tree needs roots. And this gets us back to the soup problem, because you can design the most amazing structure, but if the ground turns to liquid, none of it matters.
The Old Bay clay. It is the nemesis of San Francisco engineering.
I love that name. It sounds like a seasoning, but it's a geotechnical nightmare.
It really is. The ground there is in layers. You've got fill, sand, and then this thick, goopy layer of Old Bay clay. And the problem is, during an earthquake, that whole mix is susceptible to liquefaction.
Liquefaction, one of those terrifying words that means exactly what it sounds like. The solid ground just turns into a liquid.
It turns into quicksand. The soil loses all its stiffness. So if you build a standard foundation on that, the tower would sink, it would tilt, it could topple. You just can't rely on the mud to hold up a 1.5 million square foot building.
So you have to go deeper. You have to find bedrock.
You have to find the Franciscan bedrock. But in this location, that bedrock is 250 to 300 feet down.
That's a football field. Straight down.
And that created a huge construction crisis. The standard way to build these foundations is with drilled shafts, basically big, round, concrete-filled holes. But the equipment simply didn't exist to drill a round hole that deep through that kind of soil and keep it from collapsing.
So they hit the literal limit of the technology. They knew where they needed to go, but they didn't have the tool to get there.
So they changed the shape of the hole. They switched to something called load-bearing elements, or LBEs.
Mm-hmm.
Most people in the industry call them barrettes.
Barrettes, like a hair clip.
A very, very large hair clip. They're rectangular piles, about 5 feet wide and 10.5 feet long.
Why does making it a rectangle solve the problem?
Because it lets you use a different kind of machine. They use something called a hydrophrase.
Hydrophrase sounds like something you'd order at a smoothie shop.
It's basically a vertical trench cutter. It has these two big counter-rotating cutting wheels that just chew through the earth. But the really brilliant part isn't the cutter, it's the fluid they use. As they're digging this 300-foot deep trench, they keep it filled with bentonite slurry.
Bentonite, that's like a clay powder mixed with water, right?
Exactly. It creates this thick, heavy goo. And the density of that goo creates hydrostatic pressure against the sides of the hole. It physically pushes the mud back and keeps the trench from caving in. It's a liquid shoring system.
So you are digging blind through a swimming pool of mud 300 feet down.
Essentially, yes. You dig the hole, keep it full of slurry, then you lower this massive steel reinforcement cage into it, which is its own logistical nightmare, and then you pump concrete in from the bottom. The concrete is heavier, so it pushes all the slurry up and out.
And they had to do this how many times?
42 times. 42 of these massive rectangular roots, socketing 310 feet down into the bedrock. It's the deepest foundation system in San Francisco history.
And then you have to tie them all together, I assume, because 42 separate stilts doesn't sound very stable.
Right. They poured a massive concrete mattress on top of all of them, a foundation mat that's up to 14 feet thick in the middle. It locks all 42 roots together so they act as a single unified base.
So the tower is basically plugged directly into the bedrock, completely bypassing all that bad soil.
That's the idea. But there was one more big complication, and this one wasn't about the soil or even the building itself, it was about the neighbors.
Ah, right. You're not building in the middle of a desert. This is downtown San Francisco.
And right next door is the Transbay Transit Center, this massive transportation hub. People call it the Grand Central of the West.
Which leads to what I think of as the bad neighbor risk.
It's a huge concern. You've got this 1,000-foot tower that is designed to sway. You have its foundation pushing on the soil 300 feet down. So the people who own the transit center, they basically said, hold on, if your tower starts dancing in an earthquake, it's going to push the dirt into our foundation and damage our bus terminal.
Which is a very fair question. It's not just will you fall on us, it's will you shake the very ground we're standing on.
Yeah. The standard engineering analysis doesn't really account for that. Normally, you just model your own building and the soil it sits on. You don't usually model your neighbor.
So they had to invent a whole new kind of simulation for this.
They had to perform a soil structure interaction analysis, SSI.
Another catchy acronym.
It's incredibly complex stuff. They had to build this enormous 3D model that included not just the Salesforce Tower, but all the soil geology and the transit center and another high-rise nearby. The whole city block was treated as one interconnected system.
That must require some serious computing power.
They used software called LSDYNA, which is actually the same program car companies use for crash test simulations. They needed to see those nonlinear shock waves moving through the dirt between the buildings.
And what was the verdict? Did the tower play nice with its neighbors?
Fortunately, yes. The analysis showed that the energy transfer wouldn't destabilize the transit center. But think about the confidence you need to have in that model. You are betting a billion-dollar project on a computer simulation of how dirt moves 300 feet underground.
It really just underscores that modern engineering is as much about data and simulation as it is about steel and concrete.
It is. The math is the material. Without that specific analysis, the city might never have approved the permit.
So if we step back and look at the whole picture, we started with this flat skyline because we were, well, afraid of the dragon in the ground. We were building these short, stiff bunkers because we thought that was the only way to be safe.
And what we found out was that was a trap. That rigidity isn't the same as safety. In fact, that rigidity can be the very thing that causes the failure.
So the Salesforce Tower really represents this paradigm shift to intelligent flexibility. It's a willow tree with built-in crumple zones rooted 300 feet into bedrock, and all of it was verified by what is essentially crash test software.
It proves that we can build density safely in seismic zones. We don't have to keep sprawling out. We can build up, but only if we really respect the physics. We have to design buildings that know how to accept the energy of nature instead of just fighting it.
It's interesting. We usually think of architecture as being static, like frozen music, unmoving, a monument made of stone.
But structurally, a modern high-rise is never static. It's a machine. It has moving parts, it has fuses, it's designed to have a specific behavior.
And that's the provocative thought I'm left with. If the Salesforce Tower is safer because it's designed to move, because it's designed to yield, are we moving toward a future where our cities are more biological?
I think so, in a way. We're moving away from the Stone Age of static, rigid monuments, and we're moving toward responsive, adaptive systems. The buildings of the future will probably behave more like living organisms than they will like rocks.
A city that breathes and flexes and dances with the earth. It completely changes how you look at a skyline. It's not just a view anymore, it's a performance.
Calculus in the sky.
Calculus in the sky. I like that. So next time you're in the Bay Area, look up at that tower and remember, it isn't just standing still, it's just waiting for the music to start. Thanks for joining us on this deep dive.
My pleasure.
Stay curious, everyone. We'll see you on the next one.